So good morning all of you. So today we are entering into the third module. Just a small recap of whatever we have done so far. In the first module, we studied the basics of analog communication. We studied amplitude modulation and frequency modulation. We have seen how to generate AM signals and FM signals. We have seen how to generate amplitude modulated signals. We have studied the basics of frequency modulation. The second module, we have studied what is a random variable. We have gone through all the basic process of random variables. We have seen what is probability density function, what is cumulative density function. We have understood what is stochastic process. From now onwards, the third module will be completely different and very interesting. We'll be studying some basics of information theory and digital modulation. Okay. So let us see what is the syllabus given to us and what are the things that we have to do. We are going to begin with source coding theorems. We are going to begin with source coding theorems, theorem 1 and theorem 2. We are going to study what is meant by waveform coding. We are going to understand sampling and quantization, most important concepts for digital communication. The first method of digital communication, what we are going to study will be pulse code modulation, transmitters and receivers for PCM, what is meant by companding, what is A level and mu level, A and mu law companders. We'll be seeing DPCM, differential pulse code modulation, transmitter and receiver. We'll be studying how to design a linear predictor, Wiener-Hopf equation, what is delta modulation and what is its process, and then the slope overload. So next is the basics of communication system, what we'll be trying to understand. The first type of communication in old days was called as broadcasting. Initially we had the only intention of transmitting a signal from one point and we had so many receivers. So here, for example, let us consider a fire alarm where there is only one transmission point and it is being received. There is no two-way communication. There is no communication from the other end to the transmitter or the area from where it is going to. It is transmitting a signal. Okay. The first type of communication is called as broadcasting, like radios and televisions, where we have a transmitter and multiple receivers, where we do not have one-to-one communication or we do not have a communication from the other end back to the transmitter. Then we get these wireless talkies, where both the people can communicate, but only one at a time. You might have seen in a lot of movies and other things where you have even our Kerala police and so many other people are using this kind of wireless communicators to communicate from one end to the other. And you would have seen that after speaking for a few minutes, one person will say over. Only after the person says over, the other person will start communicating. You know why? Why is that over said, you know? Do you know that? Only one can communicate at one time from one point to the other. Okay. So what a person speaks after he says over, only then the other thing can communicate. This is called as half duplex communication, right? Only one person can communicate from one point at one particular point of time. The next one is the telephonic communication, where this is called as full duplex communication. This is one or the other. In the second case, that is in the B, only one person is communicating. In C, it is a full-fledged, full duplex communication where there are two dedicated channels one for the transmitter and the other for the receiver, in such a way that both from one point, from the point, this point, from this point to this point, and back from this point to this point, we can communicate simultaneously. And this is called as full duplex communication. Let us define what is. So let me repeat this slide. In early 1940s, Claude Shannon, who is also known as the father of digital communications, gave the first mathematical theory of communications. He gave a systematic framework. He gave certain points on how to communicate. That's what is all about source coding theorem. Okay. The main questions that were motivating on those days were how to design a communication system. What is the importance of a communication system? What is information theory? Like digital communications, information theory as a disciple came into existence after Claude Shannon's theory. Okay, it is very simple. What are the steps that can be followed so that maximum amount of information can be transmitted from one point to the other? Okay, what are the possible methods of correcting distortions available within a communication system? These are the basics that were discussed by Shannon. Okay. So basically, the name source coding itself tells you what is meant by source coding. You have a source of information, you are going to do some kind of encoding. You are going to reduce the code into very small, very small bits or a small set of information which can be further encoded, modulated, and transmitted through the channel. All the process that has been done in the transmitters has to be reversed in the receiver, obviously, so that the information returns to its original position at the receiver's end. Am I right? So what we are doing is that we are encoding the source or the information. Okay. So how to encode is what is the basics of mathematical theory of digital or information theory. And this is what is both the source coding theorems. Source coding theorem enlightens us on the different methods with which we can encode the information in such a way that it does not get distorted. What is a discrete memoryless source? So before we go ahead with source coding theorems, we need to understand what is a discrete memoryless source. So the definition goes like this, that the source output which has an unending sequence of random variables x1, x2, x3 from a finite set of x, a1, where x is equal to a1 to am, and this is called as the source alphabet. Each source output x1, x2 is selected from x using the same probability mass functions because it is a discrete function. Am I right? Because you have all discrete digital functions. Probability mass functions with px of a1 to px of am. Now we are assuming the probability mass functions to be greater than 0 for all values of j, where j is between 1 to m. That means that all the values, whatever we are going to take within the limits, is assumed to be positive. Okay, since there is no reason to assign a code word to a symbol of 0 probability and no reason to assign to model a discrete source as containing impossible symbols. We have a source, a group of sources, x1 to some xn, and this x1 to xn is taken from a random set of variable symbols, which is finite, which is from a1 to am. Okay, the probability mass functions at each point is assumed to be positive, because if it is a zero probability mass function, we don't need to transmit it, because we have no chance of that particular symbol being appearing in the other end. So what we are doing is that we are transferring symbol. A symbol is a group of bits or a set of bits. You have to understand what is a symbol. A symbol is a set of bits. So each source output x of k is statistically independent of statistically independent of the previous outputs. That is from x1 to xk minus 1. We have a set of symbols that we are going to encode and we are going to transmit. Now what we are defining is that we are defining what is meant by a discrete memoryless source. Okay. I believe that all of you can understand. Each source output x of k is statistically independent of, remember the word independent, independent of all the previous values. That is x1 to xk minus 1. Those kind of variables, that xk is called as a memoryless source. Discrete means it is not continuous, it is digital, that's it. So discrete memoryless source is a source output that is having a sequence x1 to infinity, which is taken from another set x, which is having values a1 to an. Okay, an or am, whatever it is. And this is called as the source alphabet, in such a way that the output, the source encoded output x of k is independent of all its previous values, that's starting from x1 to xk minus 1. The source coding theorem. The source coding theorem is one of the three fundamental theorems of information theory introduced by Shannon in 1948. The source coding theorem establishes a fundamental limit on the rate at which the output of an information source can be compressed without causing a large error probability. So what is the purpose of source coding theorem? Source coding theorem actually optimizes the level of compression of information, which is very popular nowadays. It reduces the information in such a way that neither the information is lost nor it has large space. So, source coding theorem 1 statement. For any discrete memoryless source with an entropy h of x, any E that is greater than 0 and any delta that is greater than 0 and any sufficiently large n, there is a fixed length source with PR, probability of failure, that is less than what is called as delta, that maps a block of n source symbols into fixed length code words of length L, which is less than the entropy plus eta plus 1 by n bits per source symbol. Shannon's theorem, fixed to fixed length source coding theorem. We consider a discrete memoryless source whose entropy is h of x. Let us consider epsilon, which is greater than 0, and delta, which is also greater than 0, any two values, and n is the total number of possible symbols in a set. There is a fixed to fixed length source code with the probability of failure that is less than or equal to delta that maps blocks of n source symbols into fixed length codes of length L, which is less than the entropy of the random variable x plus epsilon plus 1 by n bits per source symbol. Shannon's first theorem, noiseless source coding theorem, fixed to fixed length source coding theorem. Now let us consider a discrete source x of m symbols with a given distribution. The statement you have already written. Now I am going to give you some small explanation about what is the first Shannon's theorem or first source coding theorem. The average code word length can be made to approach the source entropy as close as required in such a way that the entropy h of x will be less than the L. L is the length of the possible average code word, which is less than h of x plus epsilon, where epsilon is less than 1 and is an arbitrary positive constant. And I believe that this particular slide has given you the necessary explanation for what is the noiseless source coding theorem. Any clarifications? So we'll study the converse of the first theorem also. Converse for this particular theorem for a fixed to fixed length codes. If x of n is a string of n identically independent discrete random symbols, where x of k, you have it as x of k, where k is between 1 and n, with entropy of h of x for each. In the previous theorem, fixed to fixed length codes, we have studied that there is a average code word L, which can be which is in between the entropy and entropy plus a arbitrary constant. In the converse theorem, what we are going to do is that we are going to convert a string of x raised to n into a code word, and to what extent we can compress this to that particular level. What is that maximum we can do on that? Okay. So the entropy h of x for any value of v, which is v is greater than 0, that is any positive value, it is shown that x of n can be encoded into fixed length code words of n into h of x minus v bits for every delta greater than 0 and for all sufficiently large n given the value of delta, and the probability of failure PR is given as greater than 1 minus delta minus 2 raised to minus Vn by 2. So the next noisy channel, we'll see the capacity of the channel. What is meant by capacity? If C is the capacity of the discrete channel and H the entropy per second of a discrete source, and if H is less than or equal to C, that is entropy is something that is less than the channel capacity, there will be a coding system in such a way that the output of the source can be transmitted over the channel with an arbitrarily small frequency of errors. Shannon's noisy channel coding theorem. So let me explain briefly to you what is this source coding theorem. I'm not going to go in detail because we don't have it in detail. For you guys to understand in the simplest way, it is very, very difficult. Please listen very carefully, only then you'll be able to understand. We have some positive value, we are calling it as epsilon. We have entropy of a set of symbols, we call it as h of x, where x is the random variable. Our objective is to encode this in such a way that these encoded values are being capable of being retrieved at the other end with the least possible set of errors. Okay, so Shannon describes this theorem in such a way that we can make this information so concise enough so that it is retrievable with a negligible amount of errors. So how it is being done? So what is the minimum or the minimum value of the code word of that particular length is what is being defined here. Is that clear for you, all of you? Any doubts regarding this? The next the next topic in our syllabus is waveform encoding. We have seen two theorems for encoding. Right now what we are going to do is that we are going to make these waveforms, the message signals, what we are going to derive in terms of small codes. So let us see what is waveform encoding. I'll try to explain to you after you might have noted down the points. What we are going to do is that we are going to convert this particular analog signal into a digital signal. Okay, there are three important things that happen, or three stages with which we are going to convert this particular analog signal into digital signal. The first stage is called as sampling. Second stage is called as quantization. And the third stage is where we are going to really encode the signals. The two source coding theorems what we have studied so far help us in encoding. We have different types of encoding algorithms, and most of these algorithms are very popular today. Okay, that is all about encoding. Sampling means you know that we want to convert this analog signal into digital signals. We will be taking discrete points of time in such a way that we lose the least information. We are taking samples from the waveforms. Quantization, after we take the samples, we are converting these samples into digital symbols, right? A symbol is a collection of bits, can be zeros, ones, and so on. So this is the process of sampling, quantization, and encoding altogether will convert your analog signal into a digital signal. Waveform encoding is a process of sampling, quantization, and encoding. The analog information is converted to the digital data. Waveform coding schemes are designed to reproduce the waveform output of the source at the destination with as small a distortion as possible. So the sampled, quantized, and encoded wave is transmitted and it reaches the other end. The other end, what we are supposed to do is that we need to recover the original signal back. Okay, and we'll be having some kind of errors in many stages. Say, for example, in quantization you will be having a quantization error, which might slightly distort the signal. So our objective is to reduce the distortions as much as possible. In these techniques, no attention is paid to the mechanism that produces the waveform, and all attempts are directed at the reproduction of the source output at the destination with high fidelity. Because the structure of the source plays no role in the design of waveform coders, and only properties of waveform affect the design, the waveform coders are robust and can be used with a variety of sources as long as the waveforms produced by the sources have certain similarities. So, in a nutshell, waveform encoding comprises of conversion of analog signal into a digital signal, which we are going to modulate and then transmit. Okay, this goes through three different processes. First process is called as sampling, second process is quantization, and third process is encoding. Is that clear? All of you? So the next thing what we are supposed to study is what is meant by sampling and quantization. You have, I'll just give you a small brief explanation about sampling. So let us consider a sinusoidal wave or some wave like this. This is a message signal. I wanted to convert this into a digital signal. I told you that it is a time varying process and you have a time here. You have some value of amplitude going up in this manner. Sampling is the process with which you are going to select different points. Let me change the color of the pen so that, see, these are certain points. I am selecting certain points from this particular analog signal so that I am going to work with these samples within the particular signal. Okay, the samples will contain a function of the time and the amplitude. So we are converting this analog continuous signals into discrete points of time. This is known as sampling. All of you are able to understand what is sampling? Anybody who did not understand sampling? So in the next class, we'll see in detail how we are going to sample. We are going to, today, we have seen an overview of sampling and quantization process, but in the next class, we'll mathematically derive the equations and we'll see what are the conditions with which we can sample a analog signal. Because once I start that, it will take enough time for that. So thank you all. Thank you very much.